Right now, as you read these words, the sun is destroying itself. Not slowly, not gently. Every single second, our star converts 4 million tons of its own body into pure energy and hurls it into the void. By the time you finish this sentence, another 16 million tons will have vanished forever. The sun is literally evaporating before our eyes, and it has been doing so for 4.5 billion years. We grew up thinking of the sun as eternal, constant, a golden disk that rises and sets with clockwork reliability, the very definition of permanence in our lives. Ancient civilizations worshipped it as an immortal god. Even modern humans rarely pause to consider that the thing keeping us alive is engaged in the most violent act of self-destruction in our solar system. We were taught that the sun gives us light and warmth. What they forgot to mention is the price it pays. The numbers become staggering when you extend them across time. In the hour it takes to watch this video, our star will shed over 14 billion tons of mass. In one Earth day, the sun loses 345 billion tons. Every year, that figure climbs to 126 trillion tons of solar material permanently converted into electromagnetic radiation and subatomic particles. Since the sun formed from a collapsing cloud of hydrogen gas roughly 4.6 billion years ago, it has already lost enough mass to build 300 Earth-sized planets. And yet, remarkably, impossibly, this represents less than 0.05% of its total being. What does it mean for something to lose 4 million tons every second and barely notice? How can destruction on such a scale be the very mechanism that creates the conditions for life? And perhaps most unsettling of all, what happens when this cosmic furnace finally begins to run low on fuel? These questions haunted physicists for centuries. Before Einstein, before we understood nuclear physics, the sun's energy output was one of the most baffling mysteries in all of science. Lord Kelvin, one of the most brilliant minds of the 19th century, calculated that if the sun were powered by ordinary combustion, it would have burned out after just a few thousand years. Geological evidence already showed Earth was far older than that. The sun's existence was, by all known physics, impossible. The answer, when it finally came in the 20th century, revealed something so profound about the nature of reality that it fundamentally changed our understanding of matter itself. The sun is not burning. It is doing something far more extraordinary. It is converting the fabric of existence into light. Tonight, we are going to journey into the heart of a star. We will witness temperatures that make steel evaporate like morning dew. We will explore pressures so extreme that atoms themselves surrender their identity. We will follow the path of a single photon of light as it struggles for hundreds of thousands of years to escape the stellar interior. And we will discover why the sun's apparent self-destruction is actually the most creative force in the known universe. But this is about more than astrophysics. Understanding how the sun loses mass is understanding our own origin. The calcium in your bones, the iron in your blood, the oxygen you are breathing at this very moment, all of it was forged in the heart of stars, just like our sun, or even more massive. When you look at the sun losing 4 million tons per second, you are watching the same process that created the atoms of your body. You are not merely observing a distant astronomical phenomenon. You are witnessing your own family history written in nuclear fire. If you are fascinated by the hidden violence that powers our existence, consider subscribing and hitting that thumbs up button. And here is a question for the comments. If you could witness any moment in the sun's life cycle, from its birth to its death, which moment would you choose and why? Drop your answer below, and I will pin the most creative response. What you are about to learn will forever change how you experience something as simple as standing in sunlight. That warm sensation on your skin is the end product of a process that began over 100,000 years ago deep in the solar core when hydrogen atoms were, crushed together with such violence that they merged into something new and released a tiny packet of energy that has been fighting to reach you ever since. The sun's mass loss is not a flaw or a weakness. It is the heartbeat of our solar system, the engine of all earthly life, and ultimately, the ticking clock that measures our cosmic mortality. Every photon of sunlight that touches your face carries a message written in 4 million tons of annihilated matter. Now let us begin with a truth so fundamental that it reshaped all of physics. The discovery that mass and energy are secretly the same thing, dancing in different costumes. Chapter 1. Hidden equation. The year was 1905, and a 26-year-old patent clerk in Bern, Switzerland, was about to accidentally explain how stars work. Albert Einstein was not thinking about the sun when he published his paper on special relativity. He was wrestling with the peculiar behavior of light and motion. But buried in his equations was a relationship so revolutionary that it would take decades for humanity to fully grasp its implications. Energy equals mass multiplied by the speed of light squared. E equals mc squared. 3 letters, 1 number, 1 symbol. The most famous equation in human history, and yet profoundly misunderstood by most people who recognize it. This formula does not merely describe how nuclear weapons release energy. It reveals something far deeper about the nature of existence itself. Mass and energy are not separate things. They are different manifestations of the same underlying reality. Matter is frozen energy. Energy is liberated matter. And the conversion factor between them is almost incomprehensibly enormous. Consider what that little c squared actually means. The speed of light is approximately 300 million meters per second. Square that number and you get 90 quadrillion. This is the multiplier. When you convert even a tiny amount of mass into energy, you multiply it by 90 quadrillion to find out how much energy you release. A single gram of matter, fully converted to energy, would yield 90 trillion joules, enough to power a typical American home for nearly 3,000 years. This relationship explains why the sun can lose 4 million tons every second and still survive for billions of years. The mass being lost is not disappearing into nothing. It is being converted into energy with staggering efficiency. Those 4 million tons become approximately 3.8 times 10 to the 26th watts of power, a number so large that it defies intuitive comprehension. Every second, the sun releases more energy than human civilization has produced in its entire history, multiplied by millions. But Einstein's equation alone does not tell us how this conversion happens. It merely reveals that the conversion is possible. The mechanism remained mysterious for another 3 decades, until physicists began to understand what was actually occurring in the solar core. The answer required entirely new physics, a discipline that was only just being born when Einstein published his famous paper, Quantum Mechanics. Here is what makes the sun's mass loss so conceptually strange. The sun is not burning fuel in any conventional sense. When you burn wood or coal or gasoline, you are rearranging the electron shells of atoms, breaking chemical bonds and forming new ones. These reactions release energy, but the total mass of the products is essentially identical to the mass of the reactants. Chemical burning does not destroy matter. It merely reshuffles it. The sun does something fundamentally different. It takes 4 hydrogen nuclei, each consisting of a single proton, and fuses them together to create one helium nucleus, which contains 2 protons and 2 neutrons. If you weigh the 4 hydrogen nuclei separately, then weigh the resulting helium nucleus, you discover something remarkable. The helium weighs slightly less. About 0.7% of the original mass has vanished. That missing 0.7% is the mass the sun loses. It has been converted into gamma rays, neutrinos, and kinetic energy according to Einstein's equation. The nuclear reaction is not merely releasing stored energy like a compressed spring. It is literally transforming matter into radiation. The hydrogen atoms that enter the fusion reaction are partially annihilated. They cease to exist as matter and become pure energy instead. In 1920, the British astrophysicist Arthur Eddington became one of the first scientists to connect Einstein's mass-energy equivalence to stellar power. Writing in his book, The Internal Constitution of Stars, Eddington proposed that the temperatures and pressures inside stars might be sufficient to force atomic nuclei together, releasing the binding energy that held them apart. He famously challenged skeptics who doubted such extreme conditions were possible with the observation that the sun is actually doing it. So the objections of theorists were irrelevant. Eddington was essentially correct, though the detailed mechanism would not be worked out until 1938, when Hans Bethe finally described the precise nuclear reactions powering the sun. Bethe, a German-American physicist who would later win the Nobel Prize for this work, identified two main processes, the proton-proton chain and the carbon-nitrogen-oxygen cycle. In the sun, the proton-proton chain dominates, responsible for about 99% of energy generation. What makes nuclear fusion so much more efficient than chemical burning is the strength of the forces involved. Chemical bonds are held together by electromagnetic forces between electrons. Nuclear bonds are held together by the strong nuclear force, which is approximately 100 times more powerful than electromagnetism. Breaking and reforming nuclear bonds therefore releases correspondingly more energy. To put this in perspective, burning 1 kilogram of coal releases about 30 million joules of energy. Fusing 1 kilogram of hydrogen into helium releases roughly 600 trillion joules, about 20 million times more energy from the same mass of fuel. This extraordinary efficiency is why the sun can sustain its output for billions of years, despite the seemingly catastrophic rate of mass loss. You might wonder why the sun does not simply explode. After all, you are describing continuous nuclear explosions occurring at its core. Every second, the sun converts 600 million tons of hydrogen into 596 million tons of helium, with the missing 4 million tons becoming energy. This is the equivalent of billions of hydrogen bombs detonating simultaneously. What contains this violence? The answer is gravity. The sun's enormous mass, approximately 2 octillion kilograms, creates gravitational pressure that compresses the core and contains the outward pressure from nuclear reactions. The sun exists in a state of hydrostatic equilibrium, a precise balance between the inward crush of gravity and the outward push of radiation pressure. If the fusion rate increases, the core expands slightly, which cools it down and reduces the reaction rate. If fusion decreases, gravity compresses the core, heating it up and accelerating the reactions. The sun is a self-regulating nuclear furnace, automatically adjusting to maintain stability. This equilibrium has persisted for 4.6 billion years and will continue for roughly another 5 billion. The sun is middle-aged, having consumed about half of the hydrogen in its core. When that hydrogen finally runs out, the equilibrium will fail, and our star will begin the dramatic transformation that ends in its death. But that is a story for later chapters. For now, consider what we have established. The sun's mass loss is not destruction, but transformation. 4 million tons of hydrogen becomes pure energy every second, energy that sustains every living thing on Earth. Einstein's equation, discovered in an abstract thought experiment about light and motion, turned out to describe the actual mechanism that powers stars. The universe does not waste matter. It converts it, recycling mass into radiation with elegant efficiency. This chapter has revealed the hidden relationship between mass and energy. But knowing that the sun converts matter to light does not explain how it accomplishes this feat. The conditions required for nuclear fusion are so extreme that recreating them on Earth has proven extraordinarily difficult. What exactly happens at the center of our star, where temperatures reach 15 million degrees and pressures exceed 200 billion atmospheres? Let us descend into the solar core and witness the nuclear inferno firsthand. Chapter 2. Crushing core. Imagine standing at the center of the sun. This is, of course, impossible. You would be vaporized long before you approach such a location. But in your mind, travel inward through the visible surface, through the convective zone where plasma turns in continent-sized bubbles, through the radiative zone where light struggles through dense matter, until you reach the innermost region where the actual fusion occurs. This is the solar core, and it is arguably the most extreme environment in our solar system. The core extends from the very center of the sun outward to about 25% of the solar radius, roughly 175,000 kilometers from center to edge. This region contains only about 2% of the sun's volume, yet it accounts for nearly half of the sun's mass and essentially all of its energy production. Everything that makes the sun shine originates in this compressed nuclear furnace. The temperature at the core center reaches approximately 15 million Kelvin. This is difficult to conceptualize because it is so far beyond any temperature humans experience. The hottest part of a candle flame is around 1500 Kelvin. The surface of the sun is about 5800 Kelvin. The core is over 2,500 times hotter than the visible solar surface. At these temperatures, atoms cannot exist in any recognizable form. All matter becomes plasma, a seething soup of free electrons and naked atomic nuclei stripped of their electron shells. But temperature alone is not sufficient for fusion. The hydrogen nuclei, which are simply individual protons, are all positively charged. Like charges repel each other through electromagnetic force. At room temperature, two protons brought close together would spring apart like opposing magnets. The electromagnetic repulsion between them is immense, and it increases dramatically as they approach each other. This is called the Coulomb barrier, and overcoming it is the fundamental challenge of nuclear fusion. The extreme temperature of the solar core addresses this problem by giving the protons tremendous kinetic energy. At 15 million degrees, particles are moving at hundreds of kilometers per second, colliding with enough violence to partially overcome their electromagnetic repulsion. But here's a remarkable fact. Even at these temperatures, classical physics says fusion should be impossible. The protons are still not moving fast enough to surmount the Coulomb barrier through brute force. This is where quantum mechanics enters the story. In the quantum world, particles do not have precise positions. They exist as probability clouds, smeared across space according to their wave functions. This quantum uncertainty creates a phenomenon called tunneling. A proton approaching another proton does not need to have enough energy to climb over the Coulomb barrier. Instead, it has a small but non-zero probability of simply appearing on the other side, as if it had tunneled through a wall rather than climbing over it. The probability of quantum tunneling for any individual proton collision is extraordinarily small. Most collisions result in the protons simply bouncing off each other and going their separate ways. But the Sun's core contains an almost incomprehensible number of protons undergoing an almost incomprehensible number of collisions. At any given moment, roughly 10 to the 57th power protons occupy the core region. They collide with each other billions of times per second. Even with the tiny probability of tunneling, the sheer number of attempts guarantees that fusion occurs at a steady rate. To put this in perspective, a single proton in the Sun's core will wait, on average, about 1 billion years before successfully fusing with another proton. But because there are so many protons participating, approximately 3.7 times 10 to the 38th fusion reactions occur every single second. The Sun's power output emerges from this statistical aggregation, countless individual improbable events adding up to a reliable, sustained energy source. The pressure at the core center is equally astounding. Gravity compresses the solar material to a density of about 150 grams per cubic centimeter, roughly 13 times denser than lead and 8 times denser than gold. Yet this material behaves as a gas, not a solid, because the extreme temperature prevents any crystalline structure from forming. The pressure exceeds 265 billion atmospheres, meaning the weight pressing down on each square centimeter equals 265 billion times the air pressure at Earth's sea level. This crushing pressure is essential for maintaining the core's temperature and density. Without gravity compressing the core, the plasma would expand rapidly, cooling and halting fusion. Without fusion heating the core, gravity would compress it further until a new equilibrium was reached. The balance between these forces is what determines the sun's size, luminosity, and lifespan. The proton-proton chain that dominates solar fusion is actually a multi-step process. First, two protons collide, and one of them undergoes a transformation called beta decay, converting into a neutron. The result is a deuterium nucleus, consisting of one proton and one neutron, plus a positron and a neutrino. This first step is the bottleneck that makes fusion so slow for individual particles. The probability of a proton converting to a neutron during a collision is vanishingly small, governed by the weak nuclear force, which is far weaker than electromagnetism. Once deuterium forms, subsequent steps occur much more quickly. The deuterium nucleus collides with another proton and fuses to create helium-3, which contains two protons and one neutron. Then two helium-3 nuclei collide and fuse to form helium-4, the stable form of helium, while releasing two excess protons that go on to participate in more fusion reactions. The overall process converts 4 protons into one helium-4 nucleus, releasing energy at each step. Hans Bethe worked out these reactions in meticulous detail during the late 1930s, showing exactly how much energy each step released and predicting the solar neutrino flux that should result. His calculations matched observations remarkably well, confirming that we had finally solved the ancient mystery of what powers the sun. For this achievement, Bethe received the Nobel Prize in Physics in 1967, recognition of one of the great intellectual triumphs of 20th century science. What makes the core environment so otherworldly is not just the individual extremes, but their combination. You have temperatures hotter than any natural environment in the solar system, pressures that would crush any material, densities exceeding familiar substances yet behaving like gases, and particles routinely performing quantum mechanical feats that seem to violate classical physics. The core is a realm where everyday intuition fails completely. Consider the energy density. Each cubic meter of the sun's core produces approximately 276 watts of energy through fusion. This seems remarkably low considering the extreme conditions, actually less energy per volume than a human body produces through metabolism. But the core is enormous, spanning a volume of about 2.5 times 10 to the 25th cubic meters. Multiply the modest energy density by that colossal volume, and you get the sun's total power output. This reveals something profound about the sun's inner workings. The fusion rate is actually quite gentle, spread across an enormous volume. The sun is not a bomb. It is more like a barely simmering pot, releasing its energy slowly and steadily over billions of years. If the sun's core produced energy as efficiently as a nuclear reactor per unit volume, our star would have exhausted its fuel long ago. You might wonder how scientists can claim to know what happens inside the sun when we cannot directly observe it. The answer involves multiple lines of evidence. We can model the physics of plasma, pressure, and nuclear reactions using well-tested theories. We can observe the sun's surface properties, mass, radius, and luminosity, and work backward to infer core conditions. We can detect solar neutrinos, ghostly particles that fly straight out of the core, and compare their flux to predictions. And we can study other stars and check whether our models correctly predict their behaviors. The convergence of these independent methods gives us confidence that our picture of the solar core is accurate. The core really is 15 million degrees. It really is denser than gold, yet gaseous. It really does fuse 600 million tons of hydrogen every second. The physics is not speculative. It is verified. But energy produced in the core does not instantly reach the surface. The photons created by fusion face an epic journey through the sun's interior, a journey that can take over 100,000 years. Before we can understand how the sun loses mass into space, we must follow the light on its improbable odyssey from birth to freedom. Chapter 3. Trapped light. Picture a gamma-ray photon born in the heart of the sun. It springs into existence from a fusion reaction, carrying an enormous amount of energy, vibrating at frequencies far beyond visible light. This photon is destined eventually to warm your skin on a summer afternoon. But first, it must escape from the most challenging environment imaginable, and the journey will take longer than human civilization has existed. The photon begins its flight at nearly 300 million meters per second, the universal speed of light. At this velocity, it should cross the sun's radius of 700,000 kilometers in just over 2 seconds. It should burst from the solar surface and race toward Earth in 8 minutes. The total trip from core to planet should take approximately 10 minutes. Instead, the average photon requires somewhere between 100,000 and 200,000 years to escape. The reason is simple but extraordinary. The sun's interior is opaque. Not opaque like fog, which merely dims and scatters light. Opaque like a wall, absorbing and re-emitting photons at nearly every step. The plasma in the sun's radiative zone is so dense that a photon cannot travel more than a centimeter or so before colliding with an electron or atomic nucleus and being absorbed. The particle that absorbs it then re-emits a new photon in a random direction, beginning the process again. This journey is called a random walk. The photon does not travel in a straight line toward the surface. It staggers drunkenly, bouncing left, then right, then backward, then forward, gradually diffusing outward through countless trillions of collisions. Physicist Edward L. Wright calculated that a photon is absorbed and re-emitted approximately 10 to the 25th times during its journey through the radiative zone. Each time, it loses a bit of energy, its wavelength stretching as it gradually cools from gamma-ray to X-ray to ultraviolet to visible light. Imagine the photon's perspective, if such a thing made sense. Born as the highest energy radiation in existence, it immediately slams into an electron and ceases to exist, its energy absorbed. A moment later, that electron releases a new photon, slightly less energetic, heading in a random direction. This daughter photon travels a centimeter and hits another particle. The cycle repeats endlessly. The radiative zone extends from the outer edge of the core, at about 25% of the solar radius, to roughly 70% of the radius. This region is where the epic struggle occurs. The plasma here is too cool for fusion, but still hot enough to be completely ionized. Temperatures range from about 7 million Kelvin near the core boundary to 2 million Kelvin at the outer edge. Densities drop from about 20 grams per cubic centimeter to less than 1 gram per cubic centimeter. But even this relatively rarefied material is incredibly opaque to radiation. At a certain point, around 70% of the way to the surface, the physics changes. The temperature drops below about 2 million Kelvin, and atoms begin to partially recapture their electrons. These partially ionized atoms are exceptionally good at absorbing photons, making the plasma even more opaque. Radiation can no longer transport energy efficiently. Instead, the plasma itself begins to move, carrying heat upward through convection. This is the convective zone, the sun's outer 30%. Here, hot plasma rises in giant bubbles, sometimes as large as Earth itself, carrying energy toward the surface. When it reaches the top, it cools, becomes denser, and sinks back down to be reheated. The pattern creates the granulation visible on the sun's surface. a constantly churning mosaic of bright rising cells surrounded by darker sinking lanes. The light that finally escapes from the photosphere, the visible surface of the sun, has been transformed almost beyond recognition from its origin. Those gamma rays born at 15 million degrees have been degraded into visible light, appropriate for a 5,800-degree surface. The wavelength has stretched by a factor of thousands. The individual photons have been replaced countless times, with each collision spawning a new photon of slightly less energy. What reaches your eyes is not literally the same particle that emerged from fusion. It is the great-great-grandchild, a million generations removed, carrying the same energy but in a different form. This transformation is important for life on Earth. Gamma rays are deadly radiation that would sterilize our planet. Visible light is gentle energy that drives photosynthesis and warms our oceans. The sun's opacity is not an obstacle to be overcome, but a filter that converts destructive radiation into life-giving warmth. The 100,000-year journey is a feature, not a bug. Solar scientists use a quantity called optical depth to measure how transparent or opaque a medium is. An optical depth of 1 means a photon has a 63% chance of being absorbed while passing through. The optical depth from the sun's core to its surface is approximately 10 to the 23rd, an almost incomprehensibly large number. The core is essentially a perfect prison for light, releasing it only through the gradual process of diffusion. The study of how radiation moves through matter is called radiative transfer, and it is one of the most important tools in astrophysics. By modeling the opacity of stellar material at different temperatures and densities, scientists can predict how quickly energy will flow through a star. This determines the star's luminosity, surface temperature, and evolutionary path. The 4 million tons of mass converted to energy each second only matters because that energy eventually escapes. The radiative transfer process is the bottleneck that regulates everything. You might wonder what would happen if the sun suddenly stopped fusing hydrogen. Would we notice immediately? Remarkably, no. The energy already stored in the radiative zone, trapped in its endless random walk, would continue to leak out for thousands of years. The sun would dim gradually rather than suddenly going dark. We are always seeing light that is extremely old, even though it has traveled at the fastest possible speed. There is another particle produced by fusion that does escape immediately: the neutrino. Unlike photons, neutrinos barely interact with matter. They have no electric charge and almost no mass. For a neutrino, the sun's interior is essentially transparent. Neutrinos created in the core fly straight out at nearly the speed of light, reaching Earth about 8 minutes after being produced. They pass through our planet without noticing it, flying on into interstellar space. Every second, about 65 billion solar neutrinos pass through each square centimeter of your body. Right now, as you read this, trillions of them are streaming through you, carrying direct information from fusion reactions that occurred 8 minutes ago. You are being constantly pierced by messengers from the heart of the sun, and you will never notice. Scientists have built massive underground detectors to catch the rare neutrino that does interact with ordinary matter. The Super Kamiokande detector in Japan, a tank holding 50,000 tons of ultra-pure water, detects about 15 solar neutrinos per day. The Sudbury Neutrino Observatory in Canada, the Barexino detector in Italy, and numerous other experiments have collectively confirmed that the sun's core is behaving exactly as our models predict. The neutrino flux matches theoretical calculations, providing direct evidence that we understand the solar furnace. The contrast between photons and neutrinos illuminates a profound feature of nuclear fusion. The energy released comes in 2 forms: trapped and free. The photon energy is trapped, taking epochs to escape, regulated by the sun's opacity into a steady glow. The neutrino energy is free, flying away immediately, carrying about 2% of the fusion energy into space without ever warming anything. That 2% is truly lost, gone forever into the cosmos. The remaining 98% bounces around inside the sun until it can squeeze out through the photosphere. When that ancient light finally reaches the solar surface, it does not simply float away peacefully. The photosphere is the boundary between the sun's interior and the vacuum of space. It is a transition zone where the random walk finally ends and light can travel freely. But the surface itself is a dynamic, violent place, marked by sunspots, flares, and ejections of plasma into space. The photon that spent 100,000 years escaping the radiative zone passes through this turbulent boundary layer in seconds, then leaps into the solar system at the speed of light. 8 minutes later, it reaches Earth. It might be absorbed by a leaf and drive a photosynthesis reaction. It might warm a rock or evaporate a raindrop. It might strike your retina and register as the color yellow. In that moment of absorption, the 4 million ton sacrifice of the sun finally completes its purpose. Energy created in nuclear fire, trapped for 100 millennia, converted from gamma radiation to gentle light, has crossed the void to sustain a living world. But light is not the only thing the sun sends our way. Chapter 4. Solar breath, the sun is leaking. Not just radiation, but matter itself. A continuous stream of charged particles pours outward from our star in all directions, filling the solar system with a thin plasma that flows past every planet, moon, and asteroid. This is the solar wind, and it represents another way the sun loses mass, distinct from the nuclear conversion we have already explored. Eugene Parker first proposed the existence of the solar wind in 1958, and the scientific community initially resisted his idea. Parker, a young physicist at the University of Chicago, calculated that the sun's corona, the outer atmosphere visible during eclipses, could not be in static equilibrium. The corona is fantastically hot, reaching temperatures of 1 to 2 million degrees, far hotter than the visible surface below it. At these temperatures, the corona's particles have enough energy to escape the sun's gravity and flow outward into space. Parker's prediction was confirmed just a few years later when the Mariner 2 spacecraft, traveling toward Venus, detected streams of charged particles filling interplanetary space. The solar wind was real. The sun was breathing its substance into the cosmos. The numbers involved are substantial, though not comparable to fusion losses. The solar wind carries away approximately 1.5 million tons of matter per second. This is significant, about 40% as much mass as the sun loses through nuclear conversion. But unlike the fusion mass loss, which produces useful energy, the solar wind simply carries matter away. It is pure loss, contributing to the sun's slow evaporation. The solar wind is not uniform. It has fast components and slow components, dense streams and thin ones. Near the sun's equator, the wind typically moves at about 400 kilometers per second. Near the poles, it can accelerate to 800 kilometers per second. These particles, mostly protons and electrons with some heavier ions mixed in, take several days to reach Earth and continue outward for months before reaching the outer solar system. What causes the corona to be so much hotter than the surface remains one of the most intriguing puzzles in solar physics. The photosphere is about 5,800 Kelvin. The chromosphere, the thin layer above it, is around 20,000 Kelvin. But the corona, extending millions of kilometers into space, reaches 1 to 2 million Kelvin. This is like walking away from a campfire and finding the air getting hotter instead of cooler. Something must be pumping energy into the corona, and scientists have debated the mechanism for decades. Current research points to two main heating processes. The first involves waves. Magnetic field lines threading through the solar atmosphere can carry oscillations outward from the convective zone. These waves deposit their energy in the corona as they are absorbed or dissipated. The second process involves magnetic reconnection, events where tangled magnetic field lines suddenly snap into simpler configurations, releasing stored energy explosively. Both mechanisms likely contribute, and NASA's Parker Solar Probe, launched in 2018, is flying through the corona itself to investigate. The Parker Solar Probe has achieved remarkable feats. It has flown closer to the Sun than any previous spacecraft, passing within about 8.5 million kilometers of the solar surface, while inside the orbit of Mercury. It has directly sampled the solar wind at its source, measuring particles that have traveled only hours since leaving the corona. The probe has detected magnetic switchbacks, sudden reversals in the local magnetic field direction that may be important for understanding how the solar wind accelerates. When the solar wind reaches Earth, it encounters our planet's magnetic field and wraps around it, creating a teardrop-shaped cavity called a magnetosphere. Most solar wind particles are deflected around Earth, but some funnel down along magnetic field lines near the poles, where they collide with atmospheric gases and produce the auroras. Those shimmering green and red curtains of light are visible evidence of the sun's breath touching our world. The pressure of the solar wind is extraordinarily weak by everyday standards, less than a nanopascal, a billionth of normal air pressure. But it acts continuously across enormous areas. This pressure is strong enough to push comet tails away from the Sun, creating the iconic streaming shapes we associate with comets. It is strong enough that spacecraft can theoretically sail on it, using thin reflective membranes to catch the particle and photon pressure. Japan's Icarus mission demonstrated this principle in 2010, successfully deploying a solar sail in interplanetary space. The solar wind also inflates a vast bubble called the heliosphere, the region of space dominated by solar particles rather than interstellar material. This bubble extends far beyond the orbit of Pluto, roughly 120 astronomical units from the Sun in the direction of the solar system as motion through the galaxy. At its boundary, called the heliopause, the solar wind slows, compresses, and eventually merges with the thin gas between stars. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Both spacecraft detected the expected transition, a drop in solar particle counts and an increase in cosmic rays from beyond the solar system. They confirmed that the Sun's influence has limits, that our star's breath dissipates into the greater cosmos about 20 billion kilometers from its source. For planets without protective magnetic fields, the solar wind can be devastating. Mars once had a thicker atmosphere and liquid water on its surface, but lacking a global magnetic field, it was gradually stripped by solar wind erosion. Venus, despite its proximity to the Sun, retains a dense atmosphere because of continuous volcanic outgassing, but even Venus loses atmospheric particles to the solar wind. Earth's magnetic field has preserved our atmosphere for billions of years, shielding us from this constant bombardment. The solar wind varies dramatically with solar activity. During the quiet phase of the 11-year solar cycle, the wind is relatively steady and predictable. But during solar maximum, the Sun produces coronal mass ejections, enormous eruptions that hurl billions of tons of plasma into space at speeds up to 3,000 kilometers per second. These events can compress the magnetosphere, cause geomagnetic storms, disrupt power grids, and endanger astronauts. The Carrington event of 1859 remains the most powerful geomagnetic storm in recorded history. A massive coronal mass ejection struck Earth, inducing electrical currents so strong that telegraph systems caught fire. Auroras were visible as far south as the Caribbean. If a similar event occurred today, the damage to power grids and electronic infrastructure could be catastrophic, with some estimates suggesting trillions of dollars in damages and months of recovery time. The Sun's breath is not always gentle. Yet the solar wind also provides benefits. It helps clear the inner solar system of dust and debris. It protects Earth from some galactic cosmic rays by creating a magnetic barrier at the heliosphere. It carries information about solar activity that allows us to monitor our star's behavior. And it demonstrates that stars are not isolated objects, but participants in a cosmic exchange, constantly sending matter and energy into their surroundings. The combined mass loss from nuclear conversion and solar wind totals approximately 5.5 million tons per second. This sounds enormous, and it is by any human standard. But the sun's total mass is about 2 billion tons. So losing 5.5 million tons per second barely registers. At this rate, the sun would require 10 trillion years to evaporate completely, far longer than the universe has existed. Long before that could happen, the sun will die in other ways. Still, the cumulative effect over billions of years is significant. The sun today is measurably less massive than it was when the solar system formed. This affects orbital dynamics, since planetary orbits depend on the sun's gravitational pull. As the sun loses mass, the planets very slowly spiral outward. Earth's orbit increases by about 1.5 centimeters per year. Over billions of years, this adds up to thousands of kilometers of orbital drift. More importantly, the hydrogen fuel in the sun's core is being consumed. Not just converted to energy, but genuinely used up. The helium produced by fusion accumulates in the core like ash in a fireplace. Eventually, the hydrogen will be exhausted and the sun will face a crisis. The fusion that sustains it will falter. The balance between gravity and radiation pressure will break. And our star will begin its transformation into something unrecognizable. But that fate lies billions of years in the future. For now, the sun continues its steady breath, exhaling particles into the void while its heart burns bright. The solar wind that caresses Earth today began as plasma in the corona, heated by mysterious processes, accelerated by magnetic forces, and launched on a journey that will never end. The sun is not a static object. It pulses, breathes, and evolves. Its mass loss is the rhythm of its existence. Chapter 5. Fusion Engine. We have established that the sun converts 4 million tons of mass to energy every second. We have described the crushing core where this happens. But we have not yet fully examined the nuclear reactions themselves, the specific dance of particles that transforms hydrogen into helium and releases the energy that warms our world. Understanding this process is essential because it explains not just how the sun shines, but why it shines for so long and what will eventually cause it to stop. The proton-proton chain begins with the simplest possible atomic nucleus, a single proton, which is the nucleus of hydrogen. The sun's core contains an enormous reservoir of these protons, packed together at tremendous temperature and pressure. When two protons collide with sufficient energy, they have a tiny probability of fusing together. But there is an immediate problem. Two protons cannot form a stable nucleus. A nucleus with 2 protons and 0 neutrons, called diproton, falls apart almost instantly. What saves the fusion process is the weak nuclear force. During the brief moment when 2 protons are touching, one of them can undergo beta plus decay, transforming into a neutron. This happens through the conversion of an up quark into a down quark, mediated by a W boson, a carrier particle of the weak force. The result is a nucleus containing 1 proton and 1 neutron, deuterium, also called heavy hydrogen. The reaction also produces a positron, the antimatter counterpart of an electron, and an electron neutrino. This step is the bottleneck of the entire fusion process. The probability of a proton converting to a neutron during a collision is extraordinarily small because the weak force is, well, weak. At solar core temperatures, it takes an average of 1 billion years for any individual proton to successfully complete this step. The reason the sun can sustain itself is that there are so many protons participating that enough reactions occur every second, despite the minuscule individual probability. Once deuterium forms, subsequent steps occur much faster because they are mediated by the strong nuclear force rather than the weak force. The deuterium nucleus quickly collides with another proton and fuses to form helium-3, which contains 2 protons and 1 neutron. This reaction releases a gamma-ray photon, adding to the energy output. The final step involves 2 helium-3 nuclei colliding. When they fuse, they form helium-4, the stable end product with 2 protons and 2 neutrons, while ejecting 2 excess protons. These protons return to the pool available for fusion, so the net result is that 4 protons have become 1 helium-4 nucleus. The mass difference between 4 hydrogen nuclei and 1 helium-4 nucleus is about 0.7%, and this missing mass has been converted to energy. The total energy released by converting 4 protons to 1 helium-4 nucleus is approximately 26.7 million electron volts, abbreviated MeV. About 2% of this energy escapes immediately as neutrinos, which fly out of the sun without interacting with anything. The remaining energy appears as gamma rays and kinetic energy of the product particles, which is eventually converted to the light and heat that reaches Earth. The proton-proton chain is not the only fusion pathway. In stars more massive than the Sun, the carbon-nitrogen-oxygen cycle, or CNO cycle, dominates. This process uses carbon, nitrogen, and oxygen nuclei as catalysts. Hans Bethe and Charles Critchfield worked out the details of the proton-proton chain in 1938, while Bethe independently described the CNO cycle. This work explained, for the first time in human history, why stars shine and how long they can continue doing so. The implications were revolutionary. Stars were no longer mysterious glowing objects. They were nuclear reactors whose properties could be calculated from first principles. The efficiency of nuclear fusion explains the sun's longevity. Each second, the sun converts about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons become energy. At this rate, the sun has consumed roughly half the hydrogen originally present in its core over 4.6 billion years. It has enough remaining hydrogen fuel to continue for another 5 billion years at its current luminosity. This vast timescale is a direct consequence of the slow rate of the weak force-mediated first step in the proton-proton chain. If fusion were faster, stars would burn through their fuel quickly, leaving insufficient time for life to evolve. If fusion were slower, stars might not generate enough energy to warm their planets. The actual rate of solar fusion is, in a sense, perfectly tuned to allow for the existence of living observers like ourselves. This is not a fine-tuning argument, but rather an observation that we naturally find ourselves on a planet orbiting a star whose properties permit our existence. The helium produced by fusion accumulates in the sun's core. Helium nuclei are heavier than hydrogen nuclei and sink toward the center over time. This creates a growing helium core, a ball of fusion ash that does not participate in the proton-proton chain. The temperature required to fuse helium is far higher than what the sun's core currently provides, about 100 million Kelvin compared to the present 15 million. The helium simply sits there, compressed by gravity, slowly accumulating. As the hydrogen in the core is depleted, the zone of active fusion moves outward into a shell surrounding the helium core. This process will accelerate as the sun ages, eventually causing dramatic changes in its structure. The sun will leave the main sequence, the stable phase of stellar life where hydrogen fuses in the core. It will expand into a red giant, its outer layers swelling to engulf Mercury and Venus. It will lose substantial mass through stellar winds far more powerful than the current solar wind. And eventually, it will shed its outer layers entirely, leaving behind a cooling ember called a white dwarf. But that future is 5 billion years distant. For now, the fusion engine operates steadily, converting mass to energy with clockwork precision. The core conditions are remarkably stable, maintained by the balance between gravitational compression and radiation pressure. Any fluctuation in fusion rate is automatically corrected by the resulting change in pressure and temperature. The Sun is a self-regulating nuclear furnace. Modern helioseismology, the study of sound waves traveling through the Sun, has confirmed our models of the solar interior. Just as seismologists use earthquakes to probe Earth's structure, solar physicists analyze the oscillations of the Sun's surface to infer conditions deep within. These observations show that the core is rotating slightly faster than the surface, that the transition between the radiative and convective zones is sharper than early models predicted, and that the temperature and density profiles match theoretical calculations to high precision. The standard solar model, developed over decades by physicists including John Bockle, has become one of the most successful applications of theoretical physics to a natural system. It predicts the Sun's luminosity, surface temperature, radius, and neutrino flux. It explains how energy is transported from core to surface, how the Sun's structure has evolved over billions of years, and how it will continue to evolve into the future. When observations disagreed with early versions of the model, specifically the solar neutrino problem, where detected neutrino counts were lower than predicted, the resolution came from new physics. Neutrino oscillations, which show that neutrinos change flavors as they travel. The standard solar model was vindicated, and our confidence in understanding the Sun deepened. Every second, the Sun demonstrates Einstein's equation in action. 4 million tons of matter become pure energy. That energy begins as gamma radiation in the core, diffuses outward over 100,000 years, converts to visible light at the surface, and spreads across the solar system. 8 minutes after leaving the Sun, some of it reaches Earth. Some warms the oceans. Some drives photosynthesis. Some becomes the metabolic energy that powers your reading of these words. You are, quite literally, running on sunlight. The food you ate today captured solar energy through photosynthesis. The fossil fuels that heat many homes are stored sunlight from ancient plants. Even nuclear power uses uranium forged in stellar explosions triggered by fusion. The Sun's mass loss is not an abstract astronomical process. It is the ultimate source of nearly all energy consumed on Earth. When you next feel the warmth of sunlight on your face, consider what you are receiving. Energy that cost the Sun 4 million tons of its substance. Every second energy that was born in nuclear fire 100. Millennia ago energy that traversed the void to meet you. That warmth is a gift paid for in solar mass. Chapter 6. Cosmic Context. The Sun is not special. This is one of the most profound insights of modern astronomy, a truth that simultaneously humbles and elevates our understanding. Our star is a yellow dwarf, a G-type main sequence star, one of hundreds of billions in the Milky Way galaxy alone. It loses mass through nuclear fusion and solar wind, just like countless other stars. It will eventually die just like they do. There is nothing exceptional about the Sun's physics, nothing that distinguishes it from the cosmic crowd. And yet the Sun is everything to us. It is the source of all earthly life, the engine of climate, the organizer of seasons, the clock by which civilizations have measured time. This contrast between cosmic ordinariness and local importance is central to understanding our place in the universe. The Sun matters infinitely to humanity precisely because we happen to orbit it, not because of any intrinsic uniqueness. When we examine the Sun's mass loss in context, we find that it is relatively modest. Massive stars, those 10 or more times the Sun's mass, burn through their hydrogen far faster. A star 20 times the Sun's mass might shine 100,000 times brighter and consume its fuel in just a few million years. The mass-to-energy conversion rate scales dramatically with stellar mass because more massive stars have hotter, denser cores where fusion proceeds more rapidly. Consider Betelgeuse, the red supergiant marking Orion's shoulder. This star is roughly 15 to 20 times the Sun's mass and has already exhausted the hydrogen in its core. It is now fusing helium into carbon and oxygen, a later stage of stellar evolution. Betelgeuse has expanded to enormous size, so large that if it replaced the Sun, its surface would extend past Jupiter's orbit. It loses mass through powerful stellar winds at rates perhaps 100 million times greater than the Sun's solar wind. Betelgeuse is dying, and within the next 100,000 years or so, it will explode as a supernova. At the other extreme, red dwarf stars burn so slowly that they will outlive the Sun by trillions of years. A star with 1/10 the Sun's mass has a core temperature too low for efficient fusion. It converts hydrogen to helium at a leisurely pace, taking perhaps 10 trillion years to exhaust its fuel. These stars are so common that they make up about 70% of all stars in the galaxy. None of them have died of old age yet, because the universe itself is only 13.8 billion years old. Every red dwarf that ever formed is still shining. The Sun occupies a middle ground in stellar demographics. It is massive enough to shine brightly and warm Earth to habitable temperatures, but not so massive that it burns out quickly. Its 10 billion year main sequence lifetime provides ample time for life to evolve, for intelligence to emerge, for civilizations to develop. This is not fine-tuning by any supernatural agency. It is simply the fact that we exist on a planet orbiting a star with appropriate characteristics. Stars that burn out in millions of years do not host observers pondering their mass loss. The Hertzsprung-Russell diagram, developed independently by Ejner Hertzsprung and Henry Norris Russell in the early 20th century, plots stars according to their luminosity and surface temperature. The Sun falls squarely on the main sequence, the band of stars that are fusing hydrogen in their cores. It sits near the middle of this sequence, neither particularly hot nor particularly cool, neither particularly bright nor particularly dim. It is, in astronomical terms, thoroughly average. This averageness has a corollary. The Sun's mass loss rate is typical for its stellar class. Other G-type stars lose mass at similar rates, converting similar fractions of their hydrogen to energy each second. The Sun, as 4 million tons per second, is not a special property, but a generic feature of stars at this mass and evolutionary stage. When astronomers study stellar mass loss across the galaxy, the Sun serves as a convenient reference point, well studied and close enough for detailed observation. What makes the Sun scientifically valuable is precisely its proximity. We can observe it in detail impossible for any other star. We can send probes through its corona. We can detect individual oscillations on its surface. We can resolve sunspots, flares, and prominences. This wealth of data has made the Sun the most thoroughly studied star in existence, a Rosetta Stone for understanding stellar physics more broadly. The knowledge gained from studying the Sun applies directly to other stars. The standard solar model has been generalized into stellar evolution theory, which can predict the properties and lifetimes of stars across a vast range of masses. When astronomers observe a distant star cluster and measure its color and brightness, they can infer the ages, compositions, and evolutionary states of its members by applying the same physics that explains the Sun. But here is where the cosmic context becomes unsettling. The Sun will not burn forever. Its mass loss is not merely an interesting phenomenon, but a timer counting down to an inevitable end. Every second, the Sun consumes 600 million tons of hydrogen fuel, bringing it incrementally closer to the day when the hydrogen runs out. That day is still 5 billion years away, but it is coming. When the core hydrogen is exhausted, the Sun will face a crisis. Without fusion to counteract gravity, the core will contract and heat up. The temperature will rise until hydrogen fusion ignites in a shell around the inert helium core. This shell burning will release more energy than the current core burning, causing the Sun's outer layers to expand. The Sun will become a red giant, its radius increasing by a factor of 100 or more. The surface will cool to around 4,000 Kelvin, giving it a reddish hue, but the total luminosity will increase 1,000-fold because of the vastly larger surface area. Mercury will be engulfed and vaporized. Venus will suffer the same fate. Earth's future is uncertain. Some models suggest it will be swallowed, while others indicate it might spiral outward as the sun loses mass and escape destruction. Either way, Earth's oceans will have evaporated long before, its surface baked sterile by the swelling sun. The planet that nurtured humanity will become a lifeless cinder. After 1 billion years as a red giant, the sun will exhaust the hydrogen in its shell. The core will contract further, heating until it reaches 100 million Kelvin, hot enough to fuse helium into carbon and oxygen. This helium-burning phase is relatively brief, just 100 million years or so. The sun will pulsate, losing mass through powerful stellar winds, shedding perhaps half its original mass into space. Finally, with its fuel exhausted, the sun will shed its outer layers entirely, expelling them as a glowing shell of gas called a planetary nebula. This misleading name comes from early astronomers who thought these round, fuzzy objects resembled planets. They are actually the dying breaths of stars, illuminated briefly by the hot core left behind. That core is a white dwarf, an object roughly the size of Earth, but containing half the sun's current mass. It is supported not by fusion pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. A white dwarf produces no new energy. It simply cools, gradually fading over trillions of years from white-hot to yellow to red to black. The sun's mass loss today is a preview of this end. Every ton that disappears through fusion or solar wind is material that will never be reclaimed. The ash accumulates in the core, the hydrogen dwindles, the clock ticks. The sun is, in the longest possible view, a temporary phenomenon, a bright flare in the darkness that will eventually fade. This might seem depressing, but consider the alternative perspective. The sun has been sustaining life for billions of years. It will continue for billions more. The timescales involved are so vast that they dwarf all of human history by factors of millions. We are living in the brief flowering of a star that has already given so much and will give so much more before its light finally fails. Moreover, the sun's death will seed the cosmos with enriched material. The carbon and oxygen produced in helium burning will be dispersed into space. Future generations of stars will form from gas enriched by the sun's contribution. The atoms of our sun will be recycled into new worlds, new stars, perhaps new life. Stellar death is not an end, but a transformation. The 4 million tons the sun loses each second are not wasted. They are the currency of cosmic existence, spent on sustaining planets and producing elements and shaping the galaxy. The sun is generous. It gives until it has nothing left. Chapter 7. Existential Implications. There is something profoundly unsettling about standing in sunlight once you understand what it really is. That warmth on your skin, that golden glow filtering through leaves, represents the annihilation of 4 million tons of matter every single second. You are being bathed in the light of ongoing destruction. The sun is consuming itself to keep you alive, and this arrangement has persisted for longer than your mind can genuinely comprehend. This realization forces a confrontation with impermanence on a scale that dwarfs human concerns. We worry about our mortality, measured in decades. We think about civilizations, measured in centuries or millennia. The sun operates on timescales of billions of years, yet even it is temporary. Even this colossal nuclear furnace, 1 million times the volume of Earth, will eventually go cold. If the sun itself is not eternal, what possibly could be? Philosophy has grappled with impermanence for thousands of years, but modern astrophysics has given us mathematical proof. The equations are merciless. Every fusion reaction depletes the hydrogen fuel by a measurable amount. The helium ash accumulates in the core, irreversible and inert. The countdown is not metaphorical. It is literal, calculable, inevitable. The sun has been dying since the moment it was born, and we are passengers on a planet orbiting a dying star. Yet there is something deeply beautiful in this arrangement. The sun's self-destruction is not senseless. Every ton of mass converted to energy serves a purpose. It warms Earth's surface to temperatures where liquid water can exist. It drives atmospheric circulation and ocean currents. It powers the photosynthesis that produces oxygen and organic matter. The sun is not merely dying, it is giving. Its mass loss is an act of cosmic generosity that has been sustaining life for billions of years. Consider the absurd improbability of your existence in this context. The atoms that compose your body were forged in previous generations of stars that underwent the same fusion process as the sun. Those stars reached the end of their hydrogen fuel, swelled into red giants, and expelled their enriched material into space. Some of them exploded as supernova, creating the heaviest elements through neutron capture. That stellar debris collapsed into new clouds of gas, which formed new stars, and around one of those stars, a planet coalesced from the remnants. You are made of dead stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was created through nuclear fusion in stellar cores and scattered into space when those stars died. The sun is currently engaged in the same process that created you. In a very real sense, you're watching your own origin story play out in real time, 4 million tons at a time. This connection between stellar mass loss and human existence raises profound questions about meaning and purpose. Does the universe care that stars lose mass? Does it matter in any cosmic sense that the sun is converting hydrogen to helium? From the perspective of physics, these are just natural processes, neither good nor bad, neither meaningful nor meaningless. The universe is not capable of caring, but we are capable of caring. We assign meaning even if the universe does not provide it. The sun's mass loss matters because we exist to observe it and contemplate its implications. The fact that we have evolved sufficient intelligence to understand stellar physics, to decode the mechanism that powers our own existence, is itself remarkable. We are the universe examining itself, matter that has become conscious enough to study its own origins. There is a concept in philosophy called the anthropic principle, which observes that the universe must have properties compatible with the existence of observers, or else we would not be here to observe it. This is not a supernatural claim, but a logical tautology. We find ourselves in a universe where stars last long enough for life to evolve, where fusion produces the elements necessary for chemistry, where planetary systems can form and maintain stable orbits. These conditions are necessary for our existence, so naturally we observe them. The sun's 4 million ton per second mass loss falls into this framework. If fusion were dramatically faster, stars would burn out before life could emerge. If fusion were dramatically slower, stars would not generate enough energy to warm their planets adequately. The actual rate, governed by the weak nuclear force's properties, permits the existence of observers like ourselves. We are, in a sense, calibrated to the universe we inhabit. Some people find this idea comforting, a suggestion that the universe is somehow fine-tuned for life. Others find it unsettling, implying that our existence is contingent on factors entirely beyond our control. But perhaps the most honest reaction is simply wonder. We exist in a universe where matter can arrange itself into conscious observers capable of understanding stellar physics. That is remarkable regardless of whether you interpret it as design, accident, or inevitability. The sun's mass loss also forces us to confront the concept of cosmic time. 4.5 billion years have passed since the sun ignited. Another 5 billion years remain before its hydrogen fuel runs out. These numbers are so large that they resist intuitive understanding. Human civilization is perhaps 10,000 years old. Written history covers 5,000 years. The entire span of human existence is less than 1/1,000,000th of the sun's lifetime. Try to imagine experiencing 1 second of time. Now multiply that feeling by 31 million to get 1 year. Multiply that by 4.6 billion to reach the sun's current age. Your conscious experience of time is utterly inadequate for grasping these scales. We live in the thin slice of the present, our memories extending decades into the past, our plans reaching perhaps decades into the future. The sun operates on timescales that make human concerns seem like brief flickerings. And yet, those brief flickerings matter. Consciousness, intelligence, and meaning exist within the human timescale, even if the universe operates on longer ones. The sun does not experience its own mass loss. It has no awareness of the fusion occurring at its core, no knowledge of the planets it warms, no concern for its eventual fate. We do. That difference is everything. The philosopher Alan Watts once observed that you are not something that is in the universe as a stranger, but rather the universe is inside you as your very being. When you understand stellar physics, you are not learning about something external and alien. You are discovering how the material of your body came to exist. The sun's mass loss is your origin story. The fusion of hydrogen into helium is the process that made the atoms you are built from. This creates a strange paradox. The universe is vast, ancient, and indifferent. It will continue long after the sun dies, long after the last star goes dark, long after matter itself may decay into radiation. Nothing humans do will affect these cosmic processes in any meaningful way. We are infinitesimally small, temporary, insignificant. But we are also the part of the universe that can understand this. We are matter that has become conscious, that has developed mathematics and physics, that has decoded the mechanisms governing stellar evolution. We are temporary, yes, but we are also unique. As far as we currently know, we are the only observers in this vast cosmos capable of contemplating the sun's mass loss and understanding what it means. Perhaps this is the most honest response to understanding stellar physics, a combination of humility and pride. Humility because we recognize our tiny place in an immense universe that will far outlast us. Pride because despite our size and lifespan, we have figured out how stars work. We have connected the light touching our skin to nuclear reactions occurring 93 million miles away 100,000 years ago. That is an extraordinary achievement for creatures that live less than a century. The sun loses 4 million tons every second and will continue doing so long after you are gone, long after humanity is forgotten, long after Earth itself is sterilized or destroyed. This is simultaneously the most humbling and most beautiful truth about our existence. We are temporary patterns of matter experiencing the universe for a brief moment, powered by the self-destruction of a star that neither knows nor cares that we exist. And yet, we do exist. We do experience. We do understand. For this brief window of cosmic time, matter has arranged itself into forms capable of comprehending their own origins. The sun's mass loss made that possible. Every photon of sunlight carries the energy released by nuclear fusion, energy that has powered the evolution of life from simple chemicals to conscious beings capable of studying the stars. When you stand in sunlight, you are not merely feeling warmth. You are experiencing the universe's gift of consciousness, powered by the continuous sacrifice of stellar mass. That 4 million tons per second is the price of your awareness, the cost of your existence, the fuel for your thoughts. The sun is dying so that you can live. This is not poetry. This is physics. Chapter 8. And it is human impact and observation for most of human history. The sun's mass loss was not just unknown but unknowable. Ancient civilizations worshipped the sun as a god, attributing conscious intent to its daily journey across the sky. They built temples aligned to solar cycles, developed calendars tracking its apparent motion, created mythologies explaining its power. But none of them could have guessed the mechanism. The idea that the sun was converting mass to energy would have seemed like magic or madness. The transformation from ignorance to understanding represents one of the greatest intellectual achievements in human history. It required centuries of patient observation, mathematical innovation, experimental physics, and theoretical breakthroughs. The story of how we discovered the sun's mass loss is inseparable from the story of how we learned to think scientifically about the universe. The ancient Greeks attempted to measure the sun's distance using geometry. Aristarchus of Samos, working around 270 BCE, tried to calculate the relative distances to the sun and moon by observing the timing of lunar phases. His method was sound, but his observations were too imprecise. He concluded the sun was about 19 times farther than the moon, when the actual ratio is about 400. Still, this represented the first serious attempt to quantify the sun's position rather than simply mythologizing it. For centuries afterward, progress stalled. The prevailing Ptolemaic model placed Earth at the center of the universe with the sun orbiting around it. This was not merely wrong. It was backwards in a way that made understanding the sun's true nature impossible. You cannot decode the physics of a star when your basic model of its place in the cosmos is inverted. Copernicus changed everything with his 1543 publication of De Revolutionibus Orbium Coelestium, which placed the sun at the center of the solar system. This shift in perspective was essential for future progress. Once astronomers recognized that Earth orbited the sun rather than vice versa, they could begin asking the right questions about what the sun actually was. Galileo's telescopic observations in the early 1600s revealed that the sun had spots, dark regions that moved across its surface, demonstrating that it rotated. These observations challenged the Aristotelian belief that celestial objects were perfect and unchanging. The sun was dynamic, active, variable. It had features. It was not a divine symbol, but a physical object that could be studied. The development of spectroscopy in the 19th century provided the first real insight into the sun's composition. Joseph von Fraunhofer discovered dark lines in the solar spectrum, later understood to be absorption features caused by specific elements in the sun's atmosphere. By the 1860s, scientists had identified many of these elements and realized the sun contained the same materials found on Earth: hydrogen, helium, iron, calcium, and so on. The sun was not made of some celestial substance, but ordinary matter. This raised the critical question: how was the sun producing energy? Lord Kelvin calculated that if the sun were burning conventionally, consuming coal or oil, it would last only a few thousand years. Gravitational contraction could extend this to perhaps 30 million years, but geological evidence showed Earth was much older. The sun's energy source was a genuine mystery that contradicted known physics. The breakthrough came from an unexpected direction. Einstein's 1905 special relativity paper included E equals mc, but Einstein did not immediately connect this to stellar energy. That connection was made by Arthur Eddington and others in the 1920s as quantum mechanics developed. Eddington proposed that nuclear fusion in the stellar interior could convert mass to energy, maintaining the sun for billions of years. The idea was radical and controversial. Cecilia Payne-Gaposchkin's 1925 doctoral thesis demonstrated that hydrogen was by far the most abundant element in the sun's atmosphere, making up about 73% of its mass. This was initially dismissed because it contradicted assumptions about stellar composition, but subsequent observations confirmed her analysis. If the sun was mostly hydrogen, then hydrogen fusion was the obvious candidate for the energy source. Hans Bethe finally worked out the detailed nuclear reactions in 1938, identifying the proton-proton chain as the dominant process in the sun. This achievement earned him the 1967 Nobel Prize in Physics. For the first time in human history, we understood not just that the sun was losing mass, but exactly how much and through what mechanism. The 4 million tons per second could be calculated from first principles. Modern solar physics has continued to refine this understanding. The development of neutrino detectors allowed direct observation of the sun's nuclear reactions. Raymond Davis Jr.'s chlorine detector in the Homestake mine, operating from the 1960s to the 1990s, detected solar neutrinos and demonstrated that our models were essentially correct, even though the initial neutrino counts were lower than predicted. This discrepancy, known as the solar neutrino problem, persisted for decades. It was resolved in the late 1990s when physicists demonstrated that neutrinos oscillate, changing between different flavors as they travel. The sun produces electron neutrinos that by the time they reach Earth, some have transformed into muon or tau neutrinos. Davis's detector could only see electron neutrinos, explaining the deficit. The standard solar model was vindicated. Today, we observe the sun with unprecedented precision. Spacecraft like SOHO, SDO, and the Parker Solar Probe provide continuous monitoring across multiple wavelengths. Helioseismology analyzes oscillations on the solar surface to probe the interior structure. Neutrino telescopes directly sample the products of core fusion. We understand the sun better than we understand the Earth's interior. This knowledge has practical implications. Understanding solar activity helps predict space weather, which affects satellites, power grids, and astronaut safety. The 1989 Quebec blackout was caused by a geomagnetic storm induced by a coronal mass ejection. The Carrington event of 1859 would cause far more damage today, given our reliance on electrical infrastructure. Monitoring the sun's behavior is not merely academic. It protects modern civilization. But beyond practical concerns, understanding the sun's mass loss changes our relationship with the cosmos. Previous generations saw the sun as eternal, unchanging, essentially separate from human affairs. We now know it is temporary, evolving, intimately connected to our existence. The light touching your skin today began as mass that no longer exists. You are warmed by annihilation, sustained by destruction. Humans have also begun to replicate stellar fusion on Earth. Thermonuclear weapons demonstrated that we could trigger fusion reactions, though in an uncontrolled, destructive manner. Current fusion research aims for controlled, sustained reactions that could provide clean energy. Projects like ITER and the National Ignition Facility are attempting to achieve net energy gain from fusion, effectively building miniature stars in laboratories. The challenges are immense. The sun confines its plasma through gravity, using 2 octillion kilograms of mass to create the necessary pressure. We must use magnetic fields or laser compression instead, requiring extraordinary precision. The sun sustains fusion through sheer size, allowing countless improbable quantum tunneling events to add up. We must create conditions even more extreme than the solar core to achieve practical fusion rates in small volumes. Despite decades of research and billions of dollars invested, practical fusion power remains elusive. Every few years, announcements claim we are 10 years away from commercial fusion. This has been true since the 1970s. The technical difficulties are profound. But progress continues, and recent experiments have achieved genuine breakthroughs, demonstrating that controlled fusion is possible, even if it is not yet practical. If humanity succeeds in mastering fusion, we will have learned to harness the same process that powers the sun. We will be converting mass to energy just as stars do, though on a far smaller scale. This would represent an extraordinary achievement, a species learning to replicate the fundamental mechanism of stellar power. There is something humbling about this pursuit. The sun achieves fusion effortlessly through its enormous mass and gravity. We struggle to recreate it despite our technology and understanding. The universe makes it look easy. Our best efforts produce only fleeting successes. The sun has been fusing hydrogen for 4.6 billion years without pause. We celebrate when we sustain fusion for a few seconds. This gap between understanding and implementation is characteristic of science. Knowing how something works is not the same as being able to build it. We understand stellar fusion in exquisite detail. We can calculate the reaction rates, predict the energy output, model the stellar structure. But recreating it remains extraordinarily difficult because the conditions required are so extreme. The sun's mass loss, once incomprehensible, is now one of the best understood phenomena in astrophysics. We have moved from worship to measurement, from mythology to mathematics. This transformation represents the triumph of the scientific method, humanity's most powerful tool for understanding reality. And yet, understanding does not diminish wonder. If anything, knowing how the sun works makes it more impressive. The sun is not magic, but it is magical. 4 million tons per second every second for billions of years. The scale is staggering, the precision remarkable, the consequences profound. We are the first generation of humans to truly understand our star. That is an extraordinary privilege and an awesome responsibility. Chapter 9. Cosmic Recycling. The sun's mass loss is not an isolated phenomenon. It is part of a vast cosmic cycle that has been operating since the first stars ignited in the early universe. Matter flows from stars into space, from space into new stars, from stars into planets, from planets back into space. Nothing is wasted, nothing is truly destroyed. The atoms that compose your body have been recycled through multiple generations of stars, each one contributing to the enrichment of the cosmos. In the beginning, there was only hydrogen and helium. The Big Bang, about 13.8 billion years ago, produced these two lightest elements in overwhelming abundance, with trace amounts of lithium. For roughly 400 million years, the universe was dark. No stars existed. Matter was distributed in vast clouds of primordial gas, expanding and cooling as the universe itself expanded. Gravity began to collect this gas into dense regions. Eventually, these clouds collapsed under their own weight, heating as they compressed. When the temperature and pressure became sufficient, the first stars ignited. These population 3 stars, as astronomers call them, were probably enormous, perhaps hundreds of times the sun's mass, burning fiercely and dying quickly in spectacular supernova explosions. These first supernovae changed the universe forever. They produced the first heavy elements, everything beyond hydrogen and helium. Carbon, oxygen, nitrogen, iron, gold, uranium, all of it was forged in stellar interiors and scattered by stellar deaths. The pristine hydrogen and helium gas was now contaminated with metals, using the astronomical definition, where any element heavier than helium is a metal. Subsequent generations of stars formed from this enriched gas. They contained small amounts of heavy elements in addition to their hydrogen and helium. These elements affected the star's properties, their opacity, their cooling mechanisms, their spectral features. More importantly, these elements allowed the formation of planets. You cannot make a rocky planet from pure hydrogen and helium. You need silicon, iron, oxygen, magnesium, the products of stellar nucleosynthesis. The sun is not a first-generation star. It formed from a cloud of gas that had already been enriched by previous stellar generations. The heavy elements in the sun's atmosphere, about 2% of its mass, came from stars that lived and died billions of years before the solar system existed. Those ancient stars donated their mass to the interstellar medium, and some of that material eventually collapsed to form our sun. When the sun formed, not all the gas cloud went into the star itself. About 1% remained in orbit, forming a protoplanetary disk. This disk contained dust grains made of heavy elements, silicates, and metals. These grains collided and stuck together, gradually building larger objects. Over millions of years, this material coalesced into planets, moons, asteroids, and comets. Earth is made almost entirely of elements that did not exist in the early universe. Iron, nickel, silicon, oxygen, magnesium, All of these were produced by stars and supernova. When you hold a rock, you are holding the compressed remnants of stellar explosions. When you breathe, you inhale oxygen atoms that were fused in the cores of massive stars that died billions of years ago. The carbon in organic molecules, the basis of all life on Earth, has a particularly interesting history. Carbon is produced during helium burning in red giant stars. The helium-4 nuclei fuse in pairs to form beryllium-8, which is highly unstable. But occasionally, before the beryllium-8 decays, it captures another helium-4 nucleus to form carbon-12. This process is called the triple alpha process because it effectively combines 3 helium-4 nuclei, also called alpha particles. The triple alpha process has a remarkable feature. The carbon-12 nucleus has an energy level that happens to resonate perfectly with the combined energy of beryllium-8 and helium-4. This resonance dramatically increases the probability of the reaction occurring. Without this resonance, carbon production would be far less efficient, and the universe might contain insufficient carbon for life to emerge. Fred Hoyle predicted this resonance in 1953, based purely on the observation that carbon exists in abundance. He reasoned that if carbon is common, there must be an efficient production mechanism, which implied a resonance at a specific energy level. Subsequent experiments confirmed his prediction, a stunning example of using observations to deduce fundamental physics. Once stars produce carbon, they also produce oxygen through further helium capture. Some stars produce nitrogen through the CNO cycle. Massive stars, in their final days, fuse these elements into neon, magnesium, silicon, and eventually iron. Iron represents the endpoint of fusion energy production because iron-56 is the most tightly bound nucleus. Fusing iron consumes energy rather than releasing it. When a massive star exhausts all possible fusion pathways, its iron core collapses catastrophically. In less than a second, a core roughly the size of Earth collapses to a sphere 15 kilometers across. The density becomes so extreme that protons and electrons merge into neutrons. The collapse is halted by neutron degeneracy pressure, causing the infalling material to rebound in a shock wave that blows the star apart. This supernova explosion creates elements heavier than iron through rapid neutron capture (BR) process. Freed neutrons bombard atomic nuclei, which capture them faster than they can decay. This produces unstable, neutron-rich isotopes that subsequently decay into stable heavy elements. Gold, platinum, uranium, thorium, all the elements that cannot be produced by fusion, are created in these brief, violent moments. The explosion disperses these elements into space at speeds of thousands of kilometers per second. The material plows into the surrounding interstellar gas, creating shock waves and turbulence. Over millions of years, this enriched material mixes with the ambient hydrogen and helium. New stars that form from this gas will have higher metallicity than previous generations. This cycle has been operating for over 13 billion years. Each generation of stars enriches the interstellar medium. Each new generation forms with higher heavy element content. The Sun has about twice the metallicity of stars that formed 10 billion years ago. Stars forming today have slightly higher metallicity than the Sun. This increasing enrichment makes planetary systems more likely. The first stars probably could not form rocky planets because insufficient solid material existed. The Sun formed at a time when about 1% of the galaxy's mass had been converted into heavy elements, just enough for planet formation. Future stars will find it even easier to form planets because the heavy element abundance continues to increase. The Sun participates in this cycle. Its fusion converts hydrogen to helium, enriching its core with helium ash. It also produces small amounts of heavier elements through the CNO cycle, though far less than massive stars. When the Sun eventually becomes a red giant, it will dredge up some of this enriched material and expel it through stellar winds. When it finally sheds its planetary nebula, that material will disperse into space. The carbon and oxygen produced during the Sun's red giant phase will enrich the interstellar medium by a small amount. Stars that form from that gas, billions of years in the future, will incorporate atoms that spent time inside our Sun. In a very real sense, the Sun will have descendants, not biological offspring, but chemical legacy. This perspective transforms how we think about stellar death. The Sun is not simply dying. It is contributing to the ongoing chemical evolution of the galaxy. Its mass loss today, 4 million tons per second converted to energy and 1.5 million tons expelled as solar wind, is part of this grand cycle. The Sun is simultaneously consuming itself and preparing the seeds of future creation. Earth itself is recycling material. Plate tectonics drags surface material into the mantle, where it is melted and mixed before being returned to the surface through volcanism. The oceans evaporate and rain back down. Biological organisms take up carbon, oxygen, and other elements, then release them when they die and decay. Nothing stays in one place. Everything circulates. Zoom out further, and the entire galaxy is recycling. Stars form, live, die, and scatter their remains. That material collapses into new stars. The galaxy has transformed itself multiple times over its 13 billion-year history, converting a significant fraction of its hydrogen into helium and heavy elements. This process will continue until star formation slows and eventually ceases, many trillions of years from now. You exist at a particular moment in this vast cycle. The atoms of your body were forged in stellar cores, scattered by supernova explosions, collected into a molecular cloud, incorporated into a protoplanetary disk, assembled into a planet, cycled through Earth's geology and biosphere, and temporarily organized into the pattern that is you. Someday, those atoms will be released back into the cycle, eventually finding their way into other stars, other planets, perhaps other living things. The Sun's mass loss is your participation in cosmic recycling. The energy released by converting 4 million tons of hydrogen to helium each second has sustained the chain of life that eventually produced you. That same process produced the carbon in your DNA, the calcium in your bones, the iron in your blood. You are not separate from this cycle. You are an expression of it. When you look at the Sun, you are seeing your own origin and your eventual fate. The light touching your face is the energy that makes consciousness possible. The mass being lost is the same mass that created the elements of your body. You are the universe examining itself, matter contemplating its own transformation. This is perhaps the most profound implication of understanding stellar mass loss. We are not observers standing outside the universe, studying it objectively. We are participants made of the same material, shaped by the same forces, subject to the same physics. The Sun's story is our story. Its mass loss is our existence. Chapter 10. The dying of the light 5 billion years from now. Give or take a few hundred million, the Sun will enter its final crisis. The hydrogen fuel in its core will be exhausted. The fusion reactions that have sustained it for 10 billion years will falter, and the delicate equilibrium between gravity and radiation pressure will collapse. What happens next has been calculated in extraordinary detail, modeled on computers, observed in other stars at similar evolutionary stages. We know the Sun's fate with grim certainty. The end begins not with a bang, but with a contraction. As the hydrogen runs out, fusion slows, and the core can no longer generate enough outward pressure to support the overlying layers. Gravity compresses the helium core, now about the size of Earth, but with a mass comparable to the current Sun. This compression heats the core, and the rising temperature ignites hydrogen fusion in a shell surrounding the helium. This shell burning produces more energy than the previous core burning, paradoxically. The increased luminosity pushes the outer layers outward. The Sun begins to expand. Over about 1 billion years, it will swell to roughly 200 times its current diameter, becoming a red giant. The surface will cool to around 4,000 Kelvin, giving it a deep orange-red color. But the total energy output will increase by thousands of times because of the vastly larger surface area. Mercury will be engulfed. The Sun's expanding photosphere will swallow the innermost planet, vaporizing it completely. Venus will follow. The Sun's atmosphere will extend past Earth's current orbit, though whether Earth itself is consumed depends on exactly how much mass the Sun loses during this phase. Some models suggest Earth will spiral outward and barely escape destruction. Others predict it will be swallowed. Either way, Earth is doomed long before that. As the Sun's luminosity increases, Earth's surface temperature will rise. The oceans will evaporate. The atmosphere will be stripped away by solar wind. By the time the Sun reaches red giant status, Earth will have been sterile for hundreds of millions of years, a lifeless rock baked under an increasingly violent star. Life on Earth, if it still exists in any form 5 billion years hence, will need to migrate to the outer solar system. The moons of Jupiter and Saturn, currently frozen, will become temperate as the Sun's heat reaches them. Europa's ice will melt. Titan's methane lakes will evaporate. For a brief window of cosmic time, perhaps 100 million years, these distant worlds might become habitable oases as their parent star dies. Eventually, the helium core will reach about 100 million Kelvin, hot enough to fuse helium into carbon and oxygen through the triple alpha process. This helium flash will occur suddenly, releasing as much energy in a few minutes as the Sun currently produces in 100 million years. But the core is degenerate, held up by quantum pressure, so it does not expand and cool as a normal gas would. The flash occurs under essentially constant conditions, then subsides as the core begins normal helium burning. The Sun will stabilize briefly in this helium burning phase, but the fuel is limited. Helium fusion produces far less energy per unit mass than hydrogen fusion. The Sun will exhaust its helium core in just 100 million years, about 1% of its main sequence lifetime. After that, the core will again contract, heating until it ignites helium shell burning around a carbon-oxygen core. Now the Sun has two shells burning simultaneously, helium in the inner shell, hydrogen in the outer shell. This configuration is unstable. The shells interact, causing pulsations. The Sun will vary in brightness, expanding and contracting over timescales of thousands of years. These thermal pulses will dredge up carbon from the core, bringing it to the surface where it can be observed spectroscopically. During this phase, the Sun will lose mass at a dramatic rate. The red giant's surface is so extended that the gravitational binding is weak. Stellar winds will strip away the outer layers, potentially removing half the Sun's mass over a few million years. This material will be enriched with carbon and other elements, contributing to the interstellar medium's chemical evolution. Eventually, perhaps after 1 million years of pulsations and mass loss, the Sun will expel its outer layers completely. The ejected gas will form an expanding shell, illuminated by ultraviolet radiation from the exposed core. This is a planetary nebula, one of the most beautiful phenomena in astronomy. The Ring Nebula, the Helix Nebula, the Eskimo Nebula, all of these are produced by Sun-like stars in their death throes. The planetary nebula will be visible for perhaps 50,000 years before dispersing into the interstellar medium. At its center will remain the Sun's core, now exposed to space, a white dwarf. This object will be roughly Earth-sized, containing about half the Sun's current mass compressed to astonishing density. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf will be extraordinarily hot initially, perhaps 100,000 Kelvin, radiating intense ultraviolet light. But it has no energy source. Fusion has ceased. The white dwarf simply radiates stored thermal energy, gradually cooling over trillions of years. It will fade from white to yellow to red, to eventually become a black dwarf, a cold, dark sphere of carbon and oxygen floating through space. This is the Sun's ultimate fate. Not a supernova, not a black hole, but a slow fade into darkness. The star that has sustained life on Earth for billions of years will end as a stellar ember, producing no energy, warming no planets, supporting no life. It is, in many ways, a lonely death. Other stars face different fates. Stars more than about 8 times the Sun's mass will explode as supernova, briefly outshining entire galaxies before leaving behind neutron stars or black holes. Stars less massive than the Sun will burn even longer, potentially outlasting the current age of the universe before they cool. The Sun occupies a middle category, massive enough to have an interesting life, but not massive enough for a dramatic death. This future is distant, so distant that the timescale exceeds human comprehension. 5 billion years is longer than Earth has existed. Complex life has existed for only about 500 million years. Human civilization is roughly 10,000 years old. The gap between now and the Sun's death is 500,000 times longer than all of recorded human history. And yet, it is coming. The clock is ticking. Every second, 600 million tons of hydrogen become helium. The ash accumulates. The fuel depletes. The process is gradual but inexorable. The Sun is middle-aged, having consumed about half of its core hydrogen. It is cruising toward old age with the certainty of physics. Some find this prospect depressing. The Sun, which seems so eternal in our daily experience, is actually temporary. Everything we know, every living thing on Earth, every human achievement and aspiration depends on a nuclear furnace that will eventually fail. When the Sun dies, Earth dies with it. This is not speculative. It is inevitable. But there is another perspective. 5 billion years is an almost incomprehensible amount of time. Humanity, if it survives, will have evolved into something unrecognizable. Our descendants, biological or technological, will have had billions of years to spread through the galaxy, establish colonies, develop technologies we cannot imagine. Earth may remain humanity's ancestral home, but it will not be our only home. Moreover, the Sun's death is not an ending but a transformation. The carbon and oxygen in its core will eventually disperse into space. That material will join the interstellar medium, mix with gas from other stars, and eventually collapse to form new stars and planets. The atoms that once comprised the Sun will find new configurations, new purposes, new stories. In the long view, stellar death is necessary for cosmic evolution. The first stars created heavy elements. Subsequent generations disperse those elements. Each cycle enriches the universe, increasing the complexity of available materials, allowing more intricate structures to form. Life itself is a consequence of this enrichment, impossible in the pure hydrogen-helium universe that emerged from the Big Bang. The Sun's mass loss, both its current 4 million tons per second and its eventual total dispersal as a planetary nebula, is part of this ongoing enrichment. Our star is contributing to the chemical evolution that may someday produce civilizations we cannot conceive of, living around stars that have not yet formed, thinking thoughts we cannot imagine. We began this journey with a simple number, 4 million tons per second. We end it with a profound understanding of what that number means, not just in physics but in philosophy, not just in astronomy but in meaning. The Sun is not eternal, but while it shines, it gives everything. It converts the very fabric of its being into light and warmth. It has done this for 4.6 billion years. It will continue for another 5 billion. In that span, it has enabled the evolution of life from chemistry to consciousness. It has powered the emergence of beings capable of understanding their own origins. It has made possible the very conversation we are having now. Every time you step outside into sunlight, you are experiencing nuclear physics in action. Those photons striking your skin were born in fusion reactions occurring 8 minutes ago at 93 million miles distance. They began their journey 100,000 years ago as gamma rays deep in the solar core. They struggled through endless collisions, gradually losing energy, slowly diffusing outward. They finally burst free from the photosphere and raced across the void to reach you. That warmth on your face cost the sun 4 million tons of its mass. That golden glow you see when you close your eyes toward the sun represents the annihilation of hydrogen atoms, their conversion into helium and pure energy. You are being touched by destruction. You are being warmed by transformation. You are being sustained by the most violent process in our solar system. And yet, this violence is gentle. The fusion rate is so perfectly calibrated that the sun has remained stable for billions of years. The energy production is so steady that Earth's climate has stayed within livable bounds despite cosmic timescales. The sun's self-destruction is not chaotic but controlled, not reckless but purposeful. Physics does not assign purpose, of course. The sun does not know it is warming planets. It does not intend to create conditions for life. It simply exists according to the laws of physics, fusing hydrogen because temperature and pressure are sufficient, losing mass because E equals mc squared demands it. The appearance of purpose is an artifact of observation by living things that evolved to exploit the sun's energy. But that observation itself is remarkable. We are the universe examining itself. We are matter that has become conscious enough to understand how matter behaves. The fact that we can calculate the sun's mass loss, predict its future, trace its past, connect it to our own existence, all of this represents an extraordinary achievement for a species that has existed for mere hundreds of thousands of years. The knowledge we have gained raises new questions. If the sun is temporary, what about humanity? If our star will die, what is the point of civilization, of achievement, of caring about anything when cosmic timescales dwarf all human concerns? These are ancient questions in philosophy, given new urgency by our understanding of stellar physics. Perhaps the answer is that meaning does not require permanence. You live less than a century, yet your life has meaning to you and to those who know you. Human civilization has existed for 10,000 years, yet it has meaning to us. Earth has sustained life for billions of years, and that life has intrinsic value, even if Earth will eventually be sterilized. The sun's temporary nature does not diminish its importance. If anything, it increases it. We are fortunate to exist during the narrow window when our star is stable, when Earth's orbit places us in the habitable zone, when conditions permit not just life, but intelligent life capable of understanding the cosmos. This window will not last forever, but while it does, it is everything. Another perspective is legacy. The sun will die, but not before contributing to the ongoing chemical evolution of the galaxy. The atoms it produces and disperses will become part of future stars, future planets, perhaps future life. Humanity may die, but the knowledge we have gained, the art we have created, the experiences we have had, these have intrinsic value, even if they are not eternal. We are biological observers living during a brief moment of cosmic history, on a small planet orbiting an ordinary star that is slowly consuming itself. This could be seen as diminishing, but it is actually extraordinary. Against all odds, in a vast universe of mostly empty space and dead matter, conditions aligned to produce observers capable of understanding that universe. We exist. We are aware. We comprehend our own origins. That is miraculous. The sun's mass loss is the price of our existence. 4 million tons per second, every second, for billions of years. This is the cost of consciousness, the fuel for awareness, the energy that powers every thought you have ever had. When you understand this, sunlight becomes something different. It is no longer just weather or illumination. It is a message from the heart of matter, a demonstration of the universe's most fundamental relationship. Einstein showed us that mass and energy are interchangeable. The sun demonstrates this truth every second. Beatty showed us how stars fuse hydrogen into helium. The sun has been performing this reaction for longer than Earth has existed. Parker showed us that stars breathe plasma into space. The sun's wind touches Earth daily, creating auroras and shaping our magnetic field. These insights were hard-won, the result of centuries of observation, experimentation, calculation, and insight. We stand on the shoulders of giants who decoded the mysteries of stellar physics. We benefit from their intellectual courage, their willingness to challenge assumptions, their dedication to understanding reality as it is rather than as we wish it to be. As we close, consider one final thought. 5 billion years from now, the sun will swell into a red giant. Earth will be destroyed or sterilized. The planetary system we know will be unrecognizable. But if humanity survives, if our descendants spread through the galaxy, they will carry with them the knowledge of how stars work, including our own. They will understand that their existence was made possible by a star that sacrificed 4 million tons of its mass every second to sustain life on a small blue planet. That knowledge is our legacy. The sun's gift to us is energy and existence. Our gift to the cosmos is understanding. We are the universe becoming aware of itself, matter comprehending its own transformation, consciousness emerging from nuclear fire. The sun loses 4 million tons of mass every second. This is not a fact to be memorized, but a truth to be contemplated. It is the mechanism that powers your life, the engine of your consciousness, the heartbeat of the cosmos that sustains you. When you next feel sunlight on your face, remember, you are being touched by transformation, warmed by sacrifice, sustained by the generous death of a star. That 4 million tons per second is the most precious gift in the universe, because without it, you would not exist to receive it. Thank you for joining me on this journey into the heart of our star. If you found this exploration meaningful, consider sharing it with others. The sun shines for everyone, and understanding how it shines makes the light all the more beautiful. Until next time, keep looking up, keep asking questions, keep marveling at the universe that made you possible. And remember that every photon of sunlight carries a message written in 4 million tons of annihilated matter. You are here. You are alive, and you are made of stars. Not a supernatural claim, but a logical tautology. We find ourselves in a universe where stars last long enough for life to evolve, where fusion produces the elements necessary for chemistry, where planetary systems can form and maintain stable orbits. These conditions are necessary for our existence, so naturally we observe them. The sun's 4 million ton per second mass loss falls into this framework. If fusion were dramatically faster, stars would burn out before life could emerge. If fusion were dramatically slower, stars would not generate enough energy to warm their planets adequately. The actual rate, governed by the weak nuclear force's properties, permits the existence of observers like ourselves. We are, in a sense, calibrated to the universe we inhabit. Some people find this idea comforting, a suggestion that the universe is somehow fine-tuned for life. Others find it unsettling, implying that our existence is contingent on factors entirely beyond our control. But perhaps the most honest reaction is simply wonder. We exist in a universe where matter can arrange itself into conscious observers capable of understanding stellar physics. That is remarkable regardless of whether you interpret it as design, accident, or inevitability. The sun's mass loss also forces us to confront the concept of cosmic time. 4.5 billion years have passed since the sun ignited. Another 5 billion years remain before its hydrogen fuel runs out. These numbers are so large that they resist intuitive understanding. Human civilization is perhaps 10,000 years old. Written history covers 5,000 years. The entire span of human existence is less than 1/1,000,000th of the sun's lifetime. Try to imagine experiencing 1 second of time. Now multiply that feeling by 31 million to get 1 year. Multiply that by 4.6 billion to reach the sun's current age. Your conscious experience of time is utterly inadequate for grasping these scales. We live in the thin slice of the present, our memories extending decades into the past, our plans reaching perhaps decades into the future. The sun operates on timescales that make human concerns seem like brief flickerings. And yet, those brief flickerings matter. Consciousness, intelligence, and meaning exist within the human timescale, even if the universe operates on longer ones. The sun does not experience its own mass loss. It has no awareness of the fusion occurring in its core, no knowledge of the planets it warms, no concern for its eventual fate. We do. That difference is everything. The philosopher Alan Watts once observed that you are not something that is in the universe as a stranger, but rather the universe is inside you as your very being. When you understand stellar physics, you are not learning about something external and alien. You are discovering how the material of your body came to exist. The sun's mass loss is your origin story. The fusion of hydrogen into helium is the process that made the atoms you are built from. This creates a strange paradox. The universe is vast, ancient, and indifferent. It will continue long after the sun dies, long after the last star goes dark, long after matter itself may decay into radiation. Nothing humans do will affect these cosmic processes in any meaningful way. We are infinitesimally small, temporary, insignificant. But we are also the part of the universe that can understand this. We are matter that has become conscious, that has developed mathematics and physics, that has decoded the mechanisms governing stellar evolution. We are temporary, yes, but we are also unique. As far as we currently know, we are the only observers in this vast cosmos capable of contemplating the sun's mass loss and understanding what it means. Perhaps this is the most honest response to understanding stellar physics, a combination of humility and pride. Humility because we recognize our tiny place in an immense universe that will far outlast us. Pride because despite our size and lifespan, we have figured out how stars work. We have connected the light touching our skin to nuclear reactions occurring 93 million miles away 100,000 years ago. That is an extraordinary achievement for creatures that live less than a century. The sun loses 4 million tons every second and will continue doing so long after you are gone, long after humanity is forgotten, long after Earth itself is sterilized or destroyed. This is simultaneously the most humbling and most beautiful truth about our existence. We are temporary patterns of matter experiencing the universe for a brief moment, powered by the self-destruction of a star that neither knows nor cares that we exist. And yet we do exist. We do experience. We do understand. For this brief window of cosmic time, matter has arranged itself into forms capable of comprehending their own origins. The sun's mass loss made that possible. Every photon of sunlight carries the energy released by nuclear fusion, energy that has powered the evolution of life from simple chemicals to conscious beings capable of studying the stars. When you stand in sunlight, you are not merely feeling warmth. You are experiencing the universe's gift of consciousness, powered by the continuous sacrifice of stellar mass. That 4 million tons per second is the price of your awareness, the cost of your existence, the fuel for your thoughts. The sun is dying so that you can live. This is not poetry. This is physics. And it is beautiful.